Hi, so today we will be deriving the Navier-Stokes equations. In particular, we will be taking a look into the momentum equations. So the momentum equations follows Newton's second law of motion, which is the sum of forces equals mass times acceleration. We will be doing this in 3 dimensions. So we will be taking a look at the sum of forces in the x direction, sum of forces in the y direction, m times ay, and the sum of forces in the z direction. And I would like to note that m equals the density times the volume. So for now, we'll just be focusing on the x momentum and deriving the x momentum equation. And the y momentum and z momentum will have a very similar approach. So taking a look at the mass times acceleration term, we know that max equals out to be rho ax times dv. And the reason why we have dv is because we are looking, our control volume is at an infinitesimally small. Have, let's say this is z, this is x, and then this is y. So this will be dx, dy, and dz. And that's why we have dv. So taking a look at the ax term, ax equals out to be du dt. However, u is a function of x, y, z, and t. Therefore, we would need to use chain rule to break this derivative apart. Therefore, ax equals out to be partial u, partial t, plus partial u, partial x, dx dt, dt, plus, partial v, partial y, dy dt, plus partial w, partial z, dz, dt. And looking at dx dt, dy dt, and dz dt, the change in position with respect to time is velocity, also known as for dx dt, it's u. For dy dt, it's v, and dz dt is w. So we can write that over here. Du dt equals out to be, actually, let me write it over here in a different color. Du dt equals, excuse me, dx dt equals u, dy dt equals v, dz dt equals out to be w. So our acceleration equation will look like this. Ax equals partial u partial t equals out to be plus u partial x plus v partial y plus w partial z, where partial u partial t is our local acceleration, and this term over here with the last three terms is our convective acceleration. So in total, our mass times acceleration equals out to be rho partial u partial t plus u partial t partial x plus v partial y plus w partial z. dv. So taking a look at the sum of forces now, sum of forces in the x direction term, we know that the sum of forces, or that the sum of forces in the x direction will equal out m times g of x, or any other body forces such as electromagnetic forces or gravitational forces, but for this example, we'll use gravitational force. So it's mass times acceleration in the gravitational acceleration in the x direction plus the sum of stresses. So this sum of stresses term is captured. We can capture this term by drawing our free body diagram over here. Draw that a little bit better for you guys. All right, so we'll say that here is our X, Y, and Z. And we will draw our free body diagram on the stresses acting on this control volume. So let's take a look at the X direction first. Tau XX. This will be tau XX evaluated at x plus dx. And then an opposite force on the other side is tau x evaluated at x. So basically, if we're taking a look at tau I j, we'll actually move that over here. Tau I j. I, this term, is the force that is the face that the force is acting on. Face that force is acting on. And J is direction of the force. So for this example with tau XX, this force is acting on the X plane and is also acting in the X direction. Similarly, for the Y direction, tau YX, it is acting on the Y plane, but acting in the X direction. So this will be, let me do this in a different color actually, to make it easier for you to understand. This will be tau YX evaluated at Y plus dy, whereas this will be going in the opposite direction. In our free body diagram, this will be tau YX evaluated at Y. And lastly, we'll make Z direction green. Tau ZX, tau ZX, still all the forces are going in the X direction. We are just changing the plane that the force is acting on, the face that the force is acting on. So this is tau ZX, and tau, I probably should have explained this a little bit sooner, but tau is our shear stress. Z plus dz. So here, one more. This is tau Zx evaluated at Z. Here, tau is the shear stress. So f of x, sum of the forces in the x direction will equal out to be rho gx dv plus tau xx at x plus dx minus tau xx at x. This is going in the positive direction at x plus dx, and the force at x is going negative. That's why their signs are like that in our free body diagram. And the faces that they're acting on, since we are looking at a force, this is a shear stress. So we want to multiply it by its area to get our force, so that the area that these stresses are acting on is dy dz plus tau yx at y plus dy minus tau yx at y dx dz plus tau zx at z plus dz minus tau zx at z. This will be multiplied by dx dy. And since we are subtracting the stresses at an infinitesimal volume, we get the following. This term will all be equal out to be rho gx dv plus d tau xx dy dz plus d tau yx dx dz and plus d tau zx. Dx dy. So our entire equation will be the following here. MAX equals sum of forces in the F direction will be, excuse me, it'll be rho AX dv, which equals out to be dx, dy, dz, equals out to be rho gx, dv is dx, dy, dz, plus d tau xx, dy, dz, plus d tau yx, dx, dz, plus d tau zx, dx, dy, all divided by, we can divide this whole entire equation by dx, dy, dz. And what this will give us is the following. We have rho partial u partial t plus partial u squared. Oops, excuse me. We want this other u outside. U partial x plus v partial y plus w partial z. So this will be equal out to rho gx plus partial tau xx partial x plus partial tau yx partial y plus partial tau zx partial z. So now let's focus on these three terms here. Let's focus on these terms. So we can actually separate the stresses for tau xx equals sigma xx, which is the nominal stress, minus P, and P is denoted as pressure. And we can use something called Stokes hypothesis and if you would like more detail, if you would like more detail on Stokes hypothesis, I will have a link down below to help you if you want to learn more about what this hypothesis entails. I will provide that information in a link provided below this video. So what Stokes hypothesis states is that sigma xx equals out to be 2 mu partial u partial x minus 2/3 mu partial u partial x plus partial v partial y plus partial w partial z. And Stokes hypothesis is good for compressible flows. And again, I won't be going into the exact details on how Stokes hypothesis works. We would only be applying this hypothesis for this video. But again, the link to Stokes hypothesis will be down below if you would like to learn more about that. Also, for Newtonian fluids, we have tau I j equals out to be mu partial v I partial x j plus partial vj partial x I. And I and j are just indices for general purposes. But to be more exact, what this is saying is the following. Tau xy equals tau yx equals out to be mu partial u partial y plus partial v partial x. Tau xz equals tau zx equals mu partial u partial z plus partial w partial x. And lastly, tau yz equals tau zy equals mu partial v partial z plus partial w partial y. And for the x momentum, we don't necessarily need this last identity or this last term, tau yz or tau zy. So let's move on to the following expression. So in the expression, partial tau xx partial x plus partial tau yx partial y plus partial tau zx partial z, we can say that partial tau xx partial x equals out to be negative partial p partial x plus 2 mu partial squared u partial x squared minus 2/3 mu partial x partial u partial x plus partial v partial y plus partial w partial z. For tau yx, partial tau yx, partial y, this term will equal out to be mu partial squared u partial y squared plus mu partial squared v partial u partial y. Excuse me. This will be partial y partial v partial x. And lastly, partial tau zx partial z equals out to be mu partial squared u partial z squared plus mu partial squared w, excuse me, I want to write it in terms like this, partial z partial w partial x. And I would like to note that 2 partial squared u partial x squared, I'm going to note that this will equal partial squared u partial x squared plus partial x partial u partial x. Therefore, partial tau x partial x plus partial tau yx partial y plus partial tau zx partial z equals the following. It equals out to be negative partial p partial x plus mu partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared plus 1/3 partial x partial u partial x plus partial v partial y plus partial w partial z. And the reason why that we pulled this partial x out is because in all 3 of these terms here, we use this rule, this note here, that we can pull the partial x out of this 2 of this term here, as well as we can pull this partial x out for both. So actually, let me change that. We can say that this is can actually switch this around. This will be partial x, and this will be y, and this will be z. So we can, that's why we're able to pull this partial x out of this expression. So generally, our x momentum equation states that rho partial u partial t plus u partial x plus v partial y plus w partial z equals out to be rho gx minus partial p partial x plus mu times partial squared u partial x squared plus partial squared u partial y squared plus partial squared u partial z squared plus 1/3 partial x partial u partial x plus partial v partial y plus partial w partial z. This is our x momentum, and we can apply the same approach to the y direction and z direction, and that will give us the following. The y momentum will be similar structure, but just different variables placed differently. But after I write this, you'll start to see the pattern. Partial v, partial t, plus u, partial v, partial x, plus v, oh, excuse me, I made a mistake. These are u terms over here. Yes, that was a mistake. These are u terms. So this will be v, partial y, plus w, partial v, partial z. Equals out to be rho g y, gravity in the y direction, minus partial p partial y plus mu partial squared v partial x squared plus partial squared v partial y squared plus partial squared v partial z squared plus 1/3 partial y, partial u, partial x, plus partial v, partial y, plus partial w, partial z. And lastly, for the z direction, rho partial w partial t plus u partial w partial x plus v partial w partial y plus w partial z. And let me go check one thing up here. Yes, I did make the mistake up here as well. So I want to emphasize that these terms are in fact u. Yes. Because this term goes here, this term goes, oops, not that term. Dx dt term goes here, dy dt term goes here, and dz dt term goes here. So that was my mistake. I apologize for that in advance. I made the same mistake over here. These are u and u. Ax here one more time. U and u. And I believe we are all caught up now. All right, so continuing on with this equation, we have rho g, gravitational acceleration in the z direction, minus partial p, partial z, plus mu times partial squared w, partial x squared plus partial squared w, partial y squared plus partial squared w, partial z squared plus 1/3 partial z, partial u, partial x plus partial v, partial y plus partial w, partial z. And sure, I can find a way to move these lasso select. Oops, I don't need to do that. How do I use this? There we go. Move this term down here so I can write z momentum. Perfect. And there we have it. We have the general equations for the momentum. And I'd like to note that if we are dealing with an incompressible flow, we would cancel these terms out, because recall that in the continuity equation, when we have an incompressible flow, we get the term inside of these parentheses, which equals out to be 0. Therefore, these terms cancel out. Let me write that down. Terms go to 0. Terms go to 0. For incompressible flows. Recall the continuity equation for incompressible flows. Will be partial u, partial x plus partial v, partial y plus partial w, partial z equals to 0. So if we cancel those terms out, we can write our equation in vector form. For incompressible flows, vector form. Rho times partial v partial t plus v dot gradient times v equals out to be rho g minus gradient of p plus mu dotted with second order gradient of vector v. So again, rho is our fluid velocity. This partial v partial t term is a change in velocity over time. And this term v dot gradient times v is the speed and the direction of the fluid. Rho g is the gravitational force. This could be generalized to be the body of forces acting on the control volume minus the pressure gradient, which is gradient p, and mu dotted with second order gradient times the velocity vector is the internal stress forces or the viscous effects. So here is our vector form generalized. And there we have it. That's the derivation for the Navier-Stokes momentum equations. So again, I'll have these notes free down in the link below if you would like to access these notes for your reference. If you have any questions or comments, please shoot them down below. And I plan on working on the energy equations and having those videos up to you as soon as possible. I would like to thank you so much for your attention, and please have a great rest of your day.